So it's telling you, do you want to concatenate the reads? We set it to false because these reads have already been pulled together. Because inside this fastq pulled, you have one fastq file per sample, per genome. But in some cases, per genome, per barcode, you have a lot of different fastq files, which you need to pull them together. Okay? And if you are in that scenario, you need to set that to true. And also you need to give the extension of whichever extension those files are carrying with them. In most of the cases, it's called fastq.gz in Oxford American Technologies outputs. Okay? But in this case, I have concatenated it for. If you don't do this, if you set true, it will concatenate it for you. Okay? Quite cool. And then we give the number of CPUs. I give it 12 because mine has access to it. I want to create a directory called BactFlow out underscore, I'm going to give it a unique name, underscore pre. Means this is for pre-assembly part, okay? Or let's just call it out for back out. That's it. And then you initiate the reads. So it exposes anything inside that folder. Anything inside that folder will be available. So this is going to be our working directory user. Good, good. Now we are there. So it gives you a list of your genomes. Each fastq is one genome, okay? And then here it gives you the size of them. 213 megabytes per and 1.3 gigabyte. And then what we have here, let me pull up the whole entry. So you can actually filter, like if you want to filter out, this is enough. Still, this is not enough, but this is quite good enough for assembly, depending on the genome, okay? So you might have some coverage here. So let's remove this one and turn the list. So you can play with this, okay? And then we display the read statistics. The read statistics will be displayed based on this remaining 4 genomes, okay? Here we go. This is the test statistics of your reads. So this is very good to understand how to filter your reads later on in the assembly part. So you have fastq of DNA. You have 15,000 sequences. Those sequences, you remember I talked about the shredded pieces of DNA. Those are the ones. Okay. And then eventually they need to be assembled, put together, aligned to create the consensus. A consensus and then the scaffold of your genome. Cool. And then you could also take a look at the sum of the length. If you divide this sum of the length by the length of your genome, let's say this is, I don't know, some bacteria with 2.6 megabytes per. Okay, if you divide this by 2.6 million, that will be your coverage. Okay. So if it's too much and you want to save a little bit of CPU, you can say, okay, I'm going to break this down because this has a good coverage already, like that. And minimum length is quite low. So later on, remember, when we decide on the criterion for choosing the length, minimum length, we set it to 1,000. Okay. Average length is 7,000. Max length is 47,000. And this is what I'm talking about, the length of the astronomical technology. It's magical. This is the N50. So already in 10,000 it's reaching the N50, which means I mean, it's around the average length. It's fine, it's okay, it's not very shredded. 3 pieces with N50. And these are different quantiles. The most important part is this GC content. GC content is also sometimes used just to see how different these two species are, how related they are. The same species have more or less the same GC content, okay? There are more things to talk about GC content, and if you have higher GC content, and if you have used transposon, for example, to cut your DNA, transposon has a high affinity to GC content, so it will be more shredded, okay? And things like this. But this is a bit low. It's okay. Above 50, that's when you start having a complex genome. So here you can also visualize this quality and everything by clicking on Visualize Reads. Because these genomes are basically copies of the same. I just made a little bit of changes in it. But you can see this is Oxford Nanopore Technology, and the quality, the mean quality is about 16. And you remember how we calculated the quality. For Illumina, it needs to be 30. For this, for a new flow cell that we have right now, which is good, they have improved it from around 7 to probably 16. And that's great, okay? You can download this plot by, there's some option here, somewhere. Here, you can download it like this. I did not actually work a lot with putting up some download option. Just download it as it is. And if you want to increase the dimensions and whatever, you can actually play with it. Down here, there are some size adjusting screw bars, sliding bars. Here we go. There we go. Okay? All with me. Here is interesting to look at. This is per genome read length against read quality. So all those reads that are in each genome, like the first one is called annotated, I just named it. The other one is a large genome, the other one is genome 1, and the last one is called new genome, okay? So what you can read from here, this is the histogram of your read quality, which the mean and median is about 19.5 to 20, which is great. And it has 6,512 reads with this quality, and that's great, okay? And if you go down to this density heat map and zoom in a little bit, you can see this flame of fire is not necessarily growing, you see? So length doesn't necessarily have anything to do with that. It has for the low reads from here, but in some point it peaks, so no matter how long the read becomes, the quality doesn't actually change. See what I mean? So this is also great news, like Oxford Nanopore Technology. No matter about short or long read, it can give you high quality results. This is per sample, and this is the pool of all of them. Again, you don't see any linearity here, but I have a little bit of screwness in the tail. See both on the length histogram and also on the quality histogram. But for rapid data, this is naked data. For rapid data, it actually is length dependent. So the smaller the length, the lower the quality. And I don't know, I wouldn't expect this, but I saw it on women's data recently. Yeah, this is all about this. And then we continue our next step analysis with this folder, okay? Let's run BactFlow. The first option here is true, okay? So it's checking whether BactFlow has been installed in my Conda environment or not. If it's installed, finish it, that's it. Don't do more. But I want to do assembly right now. What I do, I set this to false, and then I give the absolute path to my assembly, okay? Which is home. This time I'm giving it my own home directory because this is my sudo docker with root permission, so it has access to it. So it's called farhat fastq what was it called? Fastq pulled, right? This is the one that I've done those filtering and stuff. And it knows automatically which ones should it take. It shouldn't take from the small ones, for example. And then, should I concat the reads? No, thank you. How many CPUs do I have? I'll give it 10 because I want to use 2 CPUs. GPU, leave it. You don't use it for now. And then I want to use the same absolute directory. Let's say sm junk, okay? Inside my home directory. And then coverage filtering. You remember I said you can filter the coverage. This reads that we have was about 1.3 gigabytes maximum. It's not going to overwhelm nothing, okay? The coverage is reasonable for this genome size, so I want to set it to false. But if you want to do the coverage filtering, you need to know the genome size approximately, and also you need to have minimum of 40x coverage. And you remember what coverage was, you know? That sandwich of those trees, if you put them together, in each position, that's coverage for them. So that's important. But anyways, I'm going to set it to the default with false. Quality and read length, Definitely yes. I mean, I don't even know why they should say 4. True by default. 16 is our quality, okay? Minimum quality below 16 discarded. Above 16, yes please. And then reads below 1000 discarded. Select assembler, fly, alright? Remember those assemblers I mentioned? There you go. Fix start position to circulate the DNA again, okay? If you have a good contiguous genome, you might be able to fix the start position to how do you call it, an arbitrary gene, like DNA A, for example, chromosomal, I think, replication gene. So that's, they say, where the chromosome starts. So that's how we circulate the genome, okay? So set this to true. Publish with Madaka. In our last publication, we showed up that this is total bullshit. So discard it, unless in future they fix it. Forget about this .fasta. That's not for now. But you want to run Quest to do some post-assembly analysis. If you want to do gene annotations already in back-to-back to your assembly, you can set this to true. With Proca, if you want to do it with Bacta, you need to have its database. Not recommended for now because I don't have this database. And if you want to do taxonomy classification, assign it to a taxonomy level, you can do true. Again, you need database for it. Okay, I don't have them. For now, we want to have that FASTA file. We want to have that assembly. Later, in the post-assembly module, you can do whatever you want. Okay, and then genome completeness check-in. If true, again, you need to have its database. Heavy, time-consuming. No, thank you. And then set this to true if you want to. If sometimes the assembly fails and you did some changes and you want to resume from the previous part, always set this to true. And then we run it right now. So I'm gonna stop this. Now it's in the assembly part. Okay, people, if you're running Docker on desktop, you don't expect your terminal Docker to respond the same way. What I'm gonna do, we could stop it, or you could continue. But you see that each thing that you check, to be a task will be queued here with their name. Creates environment, testifies that environment has been created. It duplicates the reads, then goes for the fastq assembly. So we haven't set anything else to be done here. Like, of course, concatenation is false, so it's not queued there. What else? Coverage filter, if it was true, it will be queued there. Step by step. Quality length is false. If it was true, it will be queued there. Anything that you set here to false, it will be queued here. And this step takes most of the time. This is fastq assembly. It assembles all those trees, computationally very expensive. And then once your reads are ready, inside this folder, BactFlow, you can see a folder called sm out here, okay, something like this. And then inside it, there's a folder called fastas. And if you have set this, fix the start position to true. If it was true here, where is that? Fix start position of your genome. If it was true, which is true here, it will create another folder which is called circulated genome. So eventually, you will go and use that circulated genome for downstream analysis. Okay. While this is being assembled, I'm going to launch the other one, which is post-assembly, and I'll show you how to use that. This is the app for post-assembly. And in post-assembly, we have, again, only install. And you don't need to be worried in the container, okay? That's made for people who want to do it on their own computer. And I'll tell you how to download it. It's on my GitHub. Just download the whole repository and then you can use it. Genome directory, FASTA files. Okay? That's circulated FASTA genome, just the directory, the absolute path of the directory. And then genome extension, sometimes FA, sometimes FASTA, keep it FASTA. Fix start position. If you haven't done it already, you can do it here. Default is true, you can set it to false if you have already done it. Run Quest. Quest is to show how successful your assembly was, okay? So summary go. That's how a Quest report should look like. So I have only one genome in this case, okay? This is something I just made it as a dummy thing. If you had several other genomes, it would be here, okay? Each column with one genome. So it's telling you this genome is only one contig of the length 2.06 million. This is great. It is completely contiguous, one contig, one whole genome. And I'm pretty sure we know this species, it doesn't have any plasmid. So one contig, perfect assembly. It's also telling you the GC content, and it was super difficult to assemble this guy. GC content is quite high, okay? And they are very heat stable. Why? Because GC bond is hydrogen bond, and usually thermophilic bacteria, they have higher GC content. For example, back then I said GC content is important, blah, blah. All right? This one is also telling you the breakability or the contiguity. The more linear up, the more contiguous it is. Okay, this is the plot. Another one is the genome visualizer here. It shows you everything about the genome. So if I wanna zoom out like all the way out, you can see that N50 and 90, both of them are happening all across the genome. So we have only one contiguous contig. In some cases, if you have like a lot of, if it's a comparative genomics case, you have a lot, you can look at them, you can see how their N50 looks like, are they scattered, do they have plasmid or not, whatever, so on and so forth. This is for comparative genomics that creates this beautiful pangenomics circular plot, but it's very messy because right now I have how many? 8, probably 9, whatever, I don't know. Oh, sorry, now actually this is my genome. These are the GC content. 1, 2, 3, 4. I have only 4 genomes. I have plenty of space. Let's make it a little bit bigger to see how it looks, huh? How to do this. This part, this segment, is tuning parameters for this guy. So, do I add GC content? No, thank you. Do I add GC scoop? No, thank you. Resolution 200. Plot size, that is okay, but increase the width of each genome to, let's say, 5, okay? And then we display the results again. Takes a bit of time. We display the results, okay? So this display result is for this guy. But while that one is thinking, this is a cool example of if you had a taxonomy classification table, it's unparsed. You remember we talked about parsed and unparsed? It's telling me that barcode 18 is unclassified, the barcode 19 until 22 well classified up to species level, and this is average, this proportion of identity to the reference genome to which these guys have been assigned. Okay, so they have it better, obviously. You can also, it's a quite responsive table. You can also do the selections and stuff. If you want to see if there is any structural variance, okay, single nucleotide polymorphism or polynucleotide polymorphism or structural variance, whatever, you can basically go here. You have the genome directory of FASTA up there, and you want to compare all those FASTA files compared to a wild type, like their mother or something else that you have done some modifications. You do this, give the FASTA file absolute path of that FASTA genome. If you hit this, you will find this single nucleotide polymorphism, and if you want to just see all the variants, structural variants, transition, transversions, whatever, insertion, deletions, you'll run this. It doesn't show anything, but if you go to this output folder, you will find 2 folders, SMPS and SES, structural variants, okay? And then over there it will show you.
Does it annotate the variants?
Yeah, it does, like, yeah, it does actually. It's just basically a variant calling file, so you have it at the end. In some cases, you want to.
Sorry, is it possible to use it for human genome or only for prokaryotes?
Well, this one, obviously you can assemble human genomes for it and annotate, definitely.
Because
yeah.
of SMPs, just I'm wondering, is it possible?
It's definitely possible. Yeah, all the tools in it. I have seen studies that they have used these tools for human genes, especially single variant, this single nucleotide polymorphism. So in some scenarios, you want to cluster these genomes together or do some classification of genomes based on presence, absence, prevalence, or abundance of a certain gene set. Okay? That gene set, we call it an enzyme. So the enzyme table should look like this. There's two columns, one column called function, one column called enzyme. So there are several enzymes that do the same function, right? So you need to know these two roles. So you say, okay, I'm interested in these enzymes because some of my bacteria, I want to use them in a cocktail for, I don't know, for brewing some kombucha, right? Use bacteria for kombucha. Then what you're more interested in is pathways these genes that are involved in pathways of production of some acidic compounds, right? I mean, food acids, whatever. Then you find those genes and then just select them here and then give it here plus, right? Now, you know what I'm talking about when I say the enzyme file here, enzyme file, and directory to the tab delimited Bacta or Proca files. This one now is for Bacta. I will have time to create it for Proca as well. So what does this mean? When you are using Proca or Bacta, these are two common tools for prokaryotic annotation, genome annotation. It will create several files for you, including a gene bank file and a TSV, tab separated file, okay, a text file, right? Then you can basically give the directory of that annotation folder to create a folder called string finder output.